Hello everybody, I am Sravani Rani Mishra and today we are here for the first project of NAND2TETRIS. A typical computer architecture is based on a set of elementary logic gates like AND, OR, MUX, DMUX, etc. as well as their bitwise versions like AND 16, OR 16, MUX 16, etc. assuming a 16-bit machine. This project will engage you in the construction of a typical set of basic logic gates. Now, these logic gates form the elementary building blocks from which we can later construct the computer's complex CPU and RAM. Let's move forward. In this project, our objective is to build these 16 chips and yield their results. The only building blocks that we can use these projects are primitive NAND gates and the composite gates that will gradually build upon them. So we have to use only NAND gates, the most basic NAND gates, the universal gate, which can give us any other gate through its arrangements and build all the 16 gates. Now let us first start with NOT gate. As we already know what a NOT gate does, it gives us the complementary of any input we give. Now here is our script, like the code we have to tell the program as to what to do. And here we have given the input of 1. As we can see, the one input as we can see, the one input here gives us an output of 0, which is the complementary of the input. Next we have our AND gate. For AND gate, we need two inputs, which is our A and B. AND gives us a positive result or a true result only when both of its are true. So here as we can see, here the first input is 1 and the second input is 1. So our output here is 1. And this is our code file for the AND gate. Next we have our OR gate, which gives us a true when either one of the inputs are true. As you can see, both the inputs are true, so our output is 1. And here is the code file. Now our XOR gate gives us a true when both the inputs are different and a false when both the inputs are same. Here as you can see, both our A and B is 1 and 1, so our input are both same, so our output is 0, which is false. Here we are keeping a track. Next we have our MUX gate. I think it's cropped. Okay, MUX gate is like we have a lot of inputs and we have one output. We have to select any one of the inputs and give us the output. Depending on our requirement, we'll select one of the inputs. Here both are 1, all three are 1, and we select out to be 1. Similarly, we have our DMUX where our input is 1 and our selection is 1. So output will be a 0 and a 1. Not 16. Now these kind of gates are a different version of their previous gates where our input is a 16-bit input and so is our output. Here is, as we can see, our input is 4660. It's in a 16-bit format, so our output gives us 4661, which is the complement of the input. Similarly, we have other 16-bit versions for all the gates that we have learned up until now. As you can see, our inputs are all in 16-bit and our output gives us in 16-bit. Now this is our OR 16 gate, MUX 16. Everything that we have learned in normal way will also use it in 16-bit format. Now we come to our 8-way versions of the gates. Now what happens in 8-way versions is that we have 8 different inputs that needs to be ORed, or we have perform an OR operation between 8 different inputs. We don't sequentially perform it. We perform an OR operation between the first and the second input, then the third and the fourth input, and it goes like till the 8 inputs. Now from these 8 inputs we'll get 4 outputs. Now we will perform OR operation again in this 4 outputs, one for the first and second, one for the third and fourth. Now this will give us two more outputs. Now this here will perform our final OR operation, and this will be given as output. Here all the 8 inputs will be of 1 bit. Next we have our MUX 4-way 16 gate. Now, as we know what 16 depicts and what the 4-way depicts. 4-way as in will have 4 different inputs, and the 16-bit inputs, each of them will be 16-bit inputs. Now we'll perform the MUX operation on each of the 4 inputs pairwise, like the first and second, then the third and fourth, and then we perform MUX on the final output of theirs. Now each of the inputs will be of 16-bit, so we will perform with each bit. Next we have our MUX 8-way 16 gate. Now similarly, the difference is only that we'll now have 8 different inputs, and we have to go through 3 steps to get to the answer here, because first step will give us 4 answers, then it will get 2 answers, then finally we'll get our answer here. Similarly, we have DMUX 4-way. We'll perform a demultiplication operation here with 4 inputs, 4 1-bit inputs. Next we have our DMUX 8 ways. Here same thing, we have 8 different inputs, so we have to go through 3 steps to get our output, and all of the inputs are 1 bit, as we can see here in our output pins. All of them are 1 bit. Now we come to the end of the first project. I hope you understood all of the gates. Now if you're wondering why after doing all the gates we missed a very important gate, that is a NAND gate, so let me tell you, the NAND gate is considered as the primitive gate, that there is no need to implement it. Whenever a NAND chip is encountered in our HDL code, the simulator automatically invokes the built-in tools or built-in chips for its implementation. So we don't need to use that, and the rest of the things we covered. Thank you so much.